Today we're going to talk about function families. Functions of families are function types. They're the answers when you graph them. The answers all make the same general pattern. When you graph them. This year we're going to have 6 or 7 function families, but we're going to start off with some of those that you are familiar with. So the first one that we're going to look at is a linear function, and the pattern that the answers make for a linear function is a straight line. When we talk about function families, we often refer to the most basic stripped down version of that equation as the parent function. The parent function for a linear equation is y equals x. As you can see, there are no numbers here. There are numbers, but they are invisible. We talk about invisible math a lot in class. So here we have an invisible 1. So we have a slope of 1. We also have an invisible plus 0, which means we are starting our equation at 0. So when we graph our equation, we have an intercept at 0, and our slope is a 1, so it's up 1 over 1. And this is our basic linear equation. Now I want to say that a different way. If we had a input and output table, sometimes we refer to that as a T-table, a T-chart. If I were to take y equals x, when I put in a 1 for x, then y would equal 1. That's why I have an ordered pair here at 1, 1. When I put in a 2, if I put in a 2 for x, y would equal 2. So again, I have a point at 2, 2. So our pattern remains consistent, and our pattern of our answers makes a straight line. Now, when we talk about what we're going to do with this parent function, we are going to be transforming it. We're going to look at transforming our parent function. Just a review of some of the transformations that you worked on last year in geometry. We can reflect, which basically means to flip over a line. We can translate, which means to move. We can slide it left, right, up, or down. We can dilate. Which means to make bigger or smaller. And we can rotate, which basically means to turn. So when we are transforming a linear equation, we can have y equals, here's an example, plus or minus some number being multiplied by the x plus some other number. This, if it is minus, it will flip it or reflect it over the axis. So So if I were to look back up here at my original equation, and instead of y equals x, I had y equals negative x, my equation would still be a straight line, but it would reflect over the x-axis. So instead of being above, it is now below. Where it was below, now it is above. It is essentially going over this axis. This number here, which we typically use m to mean slope, rotates our line. If we look at this, let's say we had y equals 1/2 x. So we start at 0, but now we are going to go up 1 and over 2. Do you see how our blue line was rotated to be less steep? And the B results in a translation. So it slides up or down. So for example, if we had y equals x plus 3, if we graph that, I would start at 3, but our slope would still be 1. So it just looks like I took our original blue line and slid it up my graph 3 units. So when you are adding, and this is going to be pretty universal for all of our equations, when you are adding something at the end, it moves it up. If you're subtracting something at the end, it's going to move it down. Now, I know you guys are very familiar with linear equations, and you worked a little bit on in Algebra 1, our next function family, which is a quadratic equation. Quadratic equations make a different sort of pattern. They form a parabola, which essentially looks like a U. Now our parent function for a parabola is y equals x squared. You will see pretty universally our parent functions have no visible, and I stress the word visible, numbers. It's usually variables, our input and our output. There are numbers there. We could put, you all know that we have an invisible coefficient in front of the x as a 1. And if we needed to add something, we could add a 0. It doesn't change our numbers. But our parent function, in general, is going to make a U shape. And in general, parent functions are centered near the origin. I'm going to use a T-chart or an input-output table here to find our points. So if we put in a 0 for x, so y would be equal to 0 squared, then when we square 0, we still get a 0. So we have a point here at 0, 0. If I put in a 1, y equals 1 squared, I get out a 1. Please notice that I am using parentheses. It doesn't matter as much with the positive numbers, but as we've discussed, when we take out a variable, we use a set of parentheses because it's going to make a difference when we find our negative numbers. So y equals 2 squared would be 4. So we have a point at 2, 4. Now, as you can see, this is making a curve, but we were expecting a U. So I must need to work on the other side to complete my U. So I'm going to put in a -1. This is where it's very important to use your parentheses. Y is equal to +1. And when I put in a -2, y is equal to -2 squared, I get out a +4. So as you can see, I end up with a parabola. Just a reminder, this point is very important. Either the lowest or the highest point in a parabola is very important, and we refer to that as our vertex. Now, when I am looking at the transformed functions, they're going to look very similar to their parents. They're going to have a lot of features that are the same, but the general shape is going to remain a parabola. It can be skinnier, it can be fatter, it can be flipped upside down, but it will generally be a parabola. My transform function, I'm going to write this, and when you're writing your notes, I would suggest you leave a little bit of room between each item so that you have enough room to write the notes. Plus or minus a x minus h squared plus k. Each one of these things can do something different to our graph. So the first one, just like in the line, the plus or the minus helps to reflect our shape. If we have a positive shape, it is going to open upward. If we have a negative shape, it is going to open down. If we have a negative number here, it's going to open downward. That's very important when you're trying to predict, because when you're plugging in points, you need to know, should I be trying to go down or up? And that'll help you to catch any mistakes with your negatives that you make. The A influences whether it is going to be tall and skinny or short and fat. If A is a large number, if you are multiplying by a number that's greater than 1, if you put 2 here, then it will make my parabola twice as tall. It will get big more quickly. But if you have a 1/2, if you have a fraction, if you have a number less than 1, like 1/2, then it's going to slow down how fast it gets large. So it ends up making it larger. This sometimes is referred to as a vertical stretch. And this is referred to as a horizontal stretch. Think of it like you have silly putty. If I am taking a pitcher between my hands and pulling it apart horizontally, it's going to stretch it to where it's fatter. If I stretch it up and down, it's going to make it narrow and skinnier. Now, H and K have different things, but the primary thing that I want you to notice is that HK is your vertex. Now, this is very tricky. Do you see this minus here? This is going to make it look like it's the opposite number.
Could you try again?
This is going to make it look like it's the opposite number. This is going to look the same. So if I started with a transformed function that says y equals x minus 2 squared plus 3, my vertex would actually be at +2, +3. Because the minus is in the formula, my h is not -2, my h is actually +2. So in general, think inside is opposite, outside is the same. Also, the h moves my shape left and right, and my k moves it up or down. If you remember, in our linear equation, the b moved our function up. The k is doing the same thing. If it's kind of the last thing being added outside of my parentheses, it's going to move my shape up or down. Now you can always resort to doing a T-chart, but it is very helpful to know where to start, and where to start is often the vertex. So if I look at this particular equation, x, y, I think I want to do the vertex first and then work out from the middle. So if I start here in the middle, if I plug in a 2 into my equation, 2 minus 2 squared plus 3, which would be 0 plus 3, which is 3. That is my vertex, my ordered pair, which is 2, 3. And then I want to work my way up and down the number line. So here I want to put in a 1, here I want to put in a 3. So 1 minus 2 squared plus 3 would be -1 squared plus 3, which would be 4. So I have a point at 1, 4. If I had 3 minus 2 squared plus 3, which is 1 squared plus 3, which is 4. You can see here in my original one, didn't I go up 1 over 1? I'm doing that same thing again. The pattern is going to hold true because I had nothing here to change my shape. I didn't have anything to pull it out narrow or to pull it out wide. So the general shape is going to stay the same. So if I put in a 0, I would have 0 minus 2 squared plus 3, which is going to be 4 plus 3, which is 7. So I'm going to go up 3, 6, 7. Notice, here I went up 3 more. Here I went up 3 more. The pattern stayed the same. It's just that the whole parabola was moved. Let's do one more of the quadratics. We want to do one where it actually flips and maybe changes the shape a little bit. So we're going to try y equals -3x squared. Now this is going to be a larger parabola because I have just made it 3 times larger. But this time, if you notice, I am drawing my x-axis way up high. That's because I'm predicting that this negative is going to make my parabola open downward. So when you're predicting, it can help you not waste paper, not make your graph too scrunched up. So what I'm thinking is, if I have y equals -3x squared, this I'm predicting is going to make it go downward. This is a number larger than 1, so I think it's going to be a skinnier parabola than the other ones that we've done. Now, I don't have anything being added or subtracted. That my vertex here is not moved at all. My original vertex for my parent function is at the origin. Since I didn't move it at all, since it wasn't translated at all, I think it's probably still going to be at the origin. So I'm going to test that theory. So if I put in a 0, negative 3 times 0 squared would be negative 3 times 0. I do get out a 0. Okay, so I think it's going to go down from that vertex. So let's put in a 1. Negative 3 times 1 squared, which would be negative 3 times 1, which is negative 3. Let's try 2. Negative 3 times 2 squared, which would be negative 3 times 4, which is negative 12. So I'm going to have go over 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, I'm doing this side of my parabola. It's already looking very skinny compared to the other one. I need to go on the other side, so I'm going to plug in a negative 1. Negative 3 times negative 1 squared, which would be negative 3 times positive 1, is still negative 3. And we can pretty much guess that this next one's going to be negative 12. So negative 3 times negative 2 squared would be negative 3 times positive 4, which indeed is negative 12. Now here's a neat thing about a parabola. You saw me counting my way down to negative 12, but parabolas are symmetrical. So I knew if this was it was negative 12 on this side, I kind of went 2 over in the other direction. And that is my parabola. This negative flipped it downward. The 3 made it tall and skinnier than my original parent was. If you can see here, I went up once. Here I went down 3 times. So it is that 3 is tripling how much my graph is changing. Okay, our last family we're going to study for this unit is the absolute value equation. That is going to make the shape of a V. It's going to be a straight line, it's not a curve. But instead of 1 straight line, it's 2 it's kind of broken in the middle. Sometimes that's called a piecewise function because it is literally a line broken into 2 pieces. The parent function would be y equals the absolute value of x. So when we graph this, and we do our t-chart, if I put in a 0, the absolute value of 0 is 0. If I put in a 1, the absolute value of 1 is still 1. When I put in positive numbers, it doesn't change it at all. 3 is still 3. The break in my line comes when I start putting in negative numbers because the absolute value of negative 1 is equal to positive 1. The absolute value of negative 2 is equal to positive 2. And so our general shape is a V. It is 2 straight lines that meet at a vertex of 0, 0. Now, our transformed functions are going to follow a very similar pattern to our quadratic formula. It's going to be y equals plus or minus a times the absolute value of x minus h plus k. This, if it is positive, it is going to open upward. If it is negative, it is going to reflect downward, and both lines will be going down. Just like before, our A is going to change the overall shape. If it is greater than 1, it's going to be steeper. It is going to go up and down more quickly. It's going to be taller and skinnier. If it is less than 1, it's going to be fatter. It's going to go, it has a less steep slope. Our vertex will always be at HK. Again, notice that this is negative, so it's going to be the opposite number. So if I had y equals the absolute value of x minus 2 plus 3, my vertex would be at a positive 2 and a positive 3. Because this is saying x minus that number, this is saying x minus 2. So this number always looks like the opposite of what it is because my negative is in my formula. So the h does not include the negative. The h is whatever number is right here. Also, h moves left or right. So this one's going to move right 2, and the k moves things up or down. So this is going to move my graph up 3. So I'm going to know that the center, the vertex of my absolute value is going to be at 2, 3. So if I have y equals the absolute value of x minus 2 plus 3, I'm going to test my theory that I think this is going to be at 2, 3 by trying the 2 in my formula first. The absolute value of 2 minus 2 plus 3 would be the absolute value of 0 plus 3, which is just 3. 2, 3. Now I have to go on either side of this. I'm going to try a 1. The absolute value of 1 minus 2 plus 3, which is the absolute value of negative 1 plus 3, which is going to be 1 plus 3, which is 4. Now I'm going to go on the other side of my vertex, and I'm going to plug in a 3. The absolute value of 3 minus 2 plus 3, which is the absolute value of 1 plus 3, which is still 4. This is a good check. As you are moving, you should see a pattern where this is symmetrical. What you're doing on one side of the middle should be the same on either side. Please don't take a shortcut until you're very, very, very good at this, because this is a double check that you are doing it right. So I'm going to try a 0. If I have the absolute value of 0 minus 2 plus 3, I have the absolute value of negative 2 plus 3, which is 2 plus 3, which is 5. Here, I'm going to try a 4. The absolute value of 4 minus 2 plus 3, which would be 2 plus 3, which is 5. So I have my basic V shape with a vertex at 2, 3. Thank you.